we're going to postulate a fermion creation operator. We're not going to pretend to derive it from anywhere. We're going to postulate one that has the right properties. And this one is going to have the right properties for fermion single particle basis state K, or fermion mode K. And we're going to write it as BK dagger. The dagger is because it's a creation operator, and by analogy with the notation we ended up with for boson creation operators, those ones had the dagger here. And what this operator must do is it must take any state in which the single particle basis state K is empty and turn it into one in which this state K is occupied. So this is a mathematical operator that's going to perform this function. We also need the fermion creation operator to have a very particular behavior with regard to the sign of the wave function it creates, so that operations that are equivalent to swapping two particles will change the sign of the wave function. This sign behavior means we have to construct the operator with some care over signs, though in the end this is quite straightforward. These sign requirements lead to a very particular kind of commutation relation for the fermion annihilation and creation operators, an anti-commutation relation. Here we will progressively build up the properties of these operators, starting with the creation operator. So, suppose we start with the state where single particle states B and M are occupied, but the state K and all the other states are not. In the permutation notation, we therefore propose that BK dagger has the following effect on this state we've been talking about up here. So specifically, BK dagger acting on this state, which has got one particle in state B and one particle in state M, is going to turn it into this state. So BK dagger acting on this state is going to add a third particle into the system, and we propose that it adds it to the end of the list in our notation here. Adding to the end of the list is equivalent to adding a row to the bottom of the determinant and a column to the right. So now, dropping the normalization factors for convenience but keeping the sign behavior, we're going to say that BK dagger does the following thing to a determinant. It adds a row on the bottom and a column on the right. And as I said, from this point on, we're not going to bother putting in the normalization factors in our algebra. We're more interested in the sign behavior. Note that the sequence in the permutation notation is the same as the sequence down this diagonal here. So, for this particular case, with BK dagger acting on this to give us this state, the determinant is not written in standard order. We've got B, M, K as we go down here. To get this particular determinant into standard order, we need to swap the bottom two rows. And in performing this one swap, we must therefore multiply the determinant by -1. So we act with this operator BK dagger on this state. We say it adds a row on the bottom and a column on the right, and the row on the bottom has got the K's in it. And then we have to swap these two rows to get the determinant into standard order. So here's the determinant in standard order, but we've acquired a minus sign because we swapped these rows. Suppose now that we add another particle, this time in state J. Now we're going to use the operator BJ dagger to create a particle in state J, mathematically. Then we have the following behavior. Here was our BK dagger acting on this state. It gave us minus all of this here, and now we have to act with the BJ dagger operator. And that is going to give us the following state. It's going to add this row on the bottom and a column on the right, the row on the bottom with all the J's in it. We still have our minus sign from before as a result of the BK dagger acting on this state. To get to standard order now, with this result that we have just calculated by operating with these two operators on this state. We have to swap the bottom row with the adjacent row. We have to swap the j row with the m row. And in so doing, we'll be multiplying by -1. Then we swap the j row, now second from the bottom, with the adjacent k row, multiplying again by -1. So finally, -1 squared was 1, so we're left with this result. The result of bk dagger then bj dagger acting on this state gives us minus this determinant within a normalization factor. Now suppose we do this two-particle creation operation in the opposite order. First, similarly to before, but first with bj dagger now. So we're going to start with bj dagger acting on this state. And we're going to perform the necessary swap of the bottom two rows as a result. So here we have it. We've got a minus sign because we had to swap the j row that we added on the bottom with the m to get it into here. And now, next, if we operate with bk dagger, so we're operating with bk dagger after bj dagger on this state, we have our minus sign from operating with the bj dagger, and we're left with our bk dagger. We have to operate on this state now. Well, operating with bk dagger adds a row onto the bottom with k's in it and a column on the right. And we haven't done any more swaps yet, so we're still looking at the state we had before with the minus sign we had there before, but we note we've got rows that are not in order here. Now, however, we only have to swap adjacent rows once, not twice, to get the determinant into standard order. We're going to have to swap the k and m rows, but we don't have to do another swap because k is after j in the alphabet. So now the result of operating in the opposite order here with the bk dagger after the bj dagger gives us a plus sign in here and the same determinant. So this result is -1 times the result from that of the operators in the other order, that is with bk dagger first and bj dagger second. The change in sign we see here when we mathematically create the fermions in the opposite order corresponds exactly to what we want for fermion creation operators. Swapping two particles must give a change in sign for the overall fermion wave function. Creating the two particles in one order rather than the other must give a result that's equivalent to swapping the two particles in the resulting state. Note, too, that this behavior is general. We always obtain opposite signs for the results if the particles are created in the opposite order. It does not matter what the initial state is or what specific state the particles are being created in. For example, we would get the same difference in sign if we'd considered the pairs of operators bk dagger after ba dagger or ba dagger after bk dagger, or these pairs here, any particular pair that we like. Note that one of the pairs of operators always results in one more swap of adjacent rows than the other. So one of these pairs here results in one more row swap than the other one does, and the same is true for these pairs, because one of these letters is before the other in the alphabet, and hence it encounters one more row to be swapped. Hence, we have the result, valid for any state with single particle states j and k initially empty, so we can perform these creations, that bj dagger bk dagger plus bk dagger bj dagger is equal to 0, or technically the 0 operator here. But for convenience, we simply write this as a 0, because one of these gives one more swap than the other, and hence one of these leads to a minus sign compared to the other. And so the sum of the effects of both of these operators is like multiplying everything by 0, or the 0 operator. In fact, this relation turns out to be universally true for any state, as we can now show. For any state in which K is initially occupied, the fermion creation operator for that state must have the property that bk dagger acting on this state gives us 0, or a state with 0 length in the Hilbert space. Because we cannot create two fermions in one single particle state. Hence, when the single particle state K is occupied, trivially, we have that this sequence of operators acting on that state gives us 0, and this one acting on that state also gives us 0, because in both cases we're trying to create another particle in state K. And both of those must fail in the sense that the result is going to be a vector of 0 length. Hence, writing this expression down still works here because each of these terms gives us 0. So adding the two of them together gives us 0. This works for both the J states and the K states, of course. We also trivially get the same result for any initial state with J equal to K, because we're trying to create at least two fermions in the single particle state, which we can't do, and 3 if this state was already occupied. So either one of these sequences must lead to 0 if J is equal to K. So we get 0 for both of these terms, and hence we conclude that this statement here is valid for any starting state. It doesn't matter whether the starting states are empty or full. This statement is always going to be correct. A relation of this form with a plus sign in the middle is called an anti-commutation relation. It's like a commutation relation between operators, but with a plus sign in the middle rather than the minus sign we have in a commutation relation. A notation sometimes used for an anti-commutator of two operators is to use curly brackets instead of the square brackets. Now we're going to progressively develop a family of anti-commutation relations for the fermion operators. First, we have to formalize the creation operator sign behavior, and we see that with our choice that when we add a particle in state K initially to the end of the list, or equivalently to the bottom of the determinant, and then swap it into place, that the number of swaps we have to perform is the number Sk of occupied states that are after the state K in the standard order. With this definition, we have formally when bk dagger is acting on a state where the single particle state K is empty, that we will get minus 1 to the power Sk times this state where the single particle state K is now full. And this number of swaps we had to perform was simply the number of occupied states that are after the state K in the standard order.